page 11 in your packet. So I sent out a remind message yesterday. Because of Pep Rally Friday, we're going to move the test to Monday. Monday tests. We're still going to do full review day today, but tomorrow I'm going to start our next unit. Okay, so we'll do we'll do natural log, derivatives, and log properties. Obviously not on the test, but I just don't want to lose a day of instruction. Gives you an extra day extra weekend to review. Okay. But I'll still have help session Friday morning and Monday morning. Okay, Friday morning and Monday morning. Just because I don't think it takes that much time out of the classes with Pep Rally. It's just a little chaotic that day. So, all right. Let me skip number 1 and okay, let's look at number 2. Number 2 here. This is a second derivative graph here. So if we're looking at a second derivative graph, we understand that the y-axis represents something unique, right? Y-axis represents concavity. So I'm going to just label what I'm looking at here. There you go. Say. So let's create a second derivative sine line so we can kind of have a more visual understanding what we're looking at here. What can I place onto my second derivative sine line? Yeah, A and C. And what can we notate to the left of A? Yeah, I know you're looking at this, maybe saying, "Oh, this is concave down. This is not the original graph, right?" So we don't look at the shape. Look at the location. It's above the x-axis. So this is, we're going to label that as concave up. Okay. And then between A and C, below the x-axis, concave down. And then to the right of C. Yeah. So it says the function is concave up on which intervals? So, right. Sorry. So when x is less than A, when x is greater than C. Yeah. So sorry about that. That 0 looks like it's a 0 there. It's just a typo.
Not many multiple choice on the test.
Right, no multiple choice. I just found these problems for practice. Okay, so let's look at number 3. Verify that our function satisfies Rolle's theorem and find all numbers that satisfy f prime is equal to 0. So that's exactly what Rolle's theorem is trying to do, trying to determine, is there slope 0 somewhere between our endpoints? So what are our conditions for Rolle's theorem? Continuous and differentiable. So brackets around 0 and 4. Parentheses. Okay, next up, we have to confirm that the endpoints have the same what? Not the same slope, but same. Same y value, right? Same y value. If they have the same y value, then we know that they are across from each other, which means that the slope between the endpoints is going to be 0. So we're going to plug 0 and 4 into f of x. Okay. Very much like how you would handle mean value theorem, right? You're always just finding order pairs and finding slope, right? No calculus just yet. So what's f of 0 equal to? What's f of 4 equal to? 1 as well. So yeah, if they have the same y value, that means the slope between these two endpoints will be what? 0. Slope is 0. My average rate of change is 0. And if you want to convince yourself of that, just go through slope formula, right? 1 minus 1, sorry. Change in y over change in x. So 0 over 4 is 0. Okay, so now it's a guarantee, right? There must be a place on this curve where there's a slope 0 between 0 and 4. We can just set f prime equal to 0 and solve for c. F prime is easy, power rule. So that means at c equals 2, or when x is equal to 2, this curve is going to experience a slope 0. And this location is safely between my endpoints. C equals 2, yep. Okay, let's skip to the next page here. Let's do see if we can identify what theorem this one is.
So why didn't you 1 minus 1 over 4 minus 0 without that?
Oh, just to show that the slope between the endpoints is 0. Because I don't want students to set their f prime equal to 1. I want them to set it equal to 0.
Like the q, like y values on top of the 2.
Right, changing y over changing x slope. Thank you. Okay, so page 12. It says the height of the object is provided with x of t, that's position. Find the average velocity. So average velocity, that just means change in position over change in time, right? Just slope between the endpoints. So first 4 seconds, that means I'm going from what to what? 0 to 4.
How would be like max value?
Yeah. So we'll do x of 4 equals to x of 0 equals 2. X of 4 equals 2. Right. Change in position over change in time, just like how we would do finding slope between endpoints. Okay, so 0 in for t. What's our y value there? 500. Okay, use your calculator, plug 4 in. So my average rate of change, or in this case, my average velocity, change in y over change in x, or in this case, change in position over change in time. What's our average velocity? What's our average rate of change?
I guess I need like. Oh yeah, or no, 0.
Yeah, so subtract in your calculator and divide by 4. What'd you guys get? Okay, so that means between 0 and 4 seconds, this object has an average velocity of negative 19.6 meters. So can we guarantee that somewhere between 0 and 4 seconds, this object is going to reach exactly this velocity? Yes, right. And that's basically, that's what we're about to do here, mean valley theorem. So it says mean valley theorem to look for, okay, I know my average velocity is this value. When is this object going to hit exactly negative 19.6 meters per second? So all we do is we just set the derivative equal to our average rate of change, and then we just solve for x. So in this case, solve for t. So we set our average rate of change equal to the instantaneous rate of change. Okay. We have our average velocity. We just have to figure out our velocity function or our derivative. So what's x prime of t? What's our velocity function? Yeah. So just set them equal to each other, right? Because we were asking, when is this object going to reach a velocity of negative 19.6? Set them equal to each other, and then we just solve for t. Now it says find the time and the height. So we know that this object is going to reach this velocity at 2 seconds, but it's asking, well, how high is this object going to be at that moment in time? So we just have to plug 2 back into the what? Into the original, yeah. So this is just an application of mean valley theorem. Find the slope, find the derivative, set them equal to each other.
The y value.
Yeah, the y value is your height. Okay, let's turn to page. Let's do a full derivative problem here. Page. We'll do page. Okay, page 7, and then we'll do page 8. Okay, page 7 and page 8. Okay, we have a full derivative problem here. Let's start off by building our derivative sine line, as well as our second derivative sine line. The one thing that we haven't quite gone over is how does this range fit into our problem? Let's talk about that once you sketch your derivative graph using dotted lines. Okay, so once you have that dotted line graph, I'm going to show us how we can adjust it to fit this range. Okay, but go ahead and start, and then I'll work through the problem alongside you guys. Okay, how do our F prime graph look? Or sorry, F prime sign line look? Look good? Okay, F double prime, and now you're gonna target points of inflections, which are not gonna be x-intercepts on the F prime. Now we're looking at the what? Yeah, max and mins, right? The peaks and valleys. I'll highlight those points.
Some of them overlap.
That's right. Some overlap, but that's okay, right? An x-intercept can be a peak or valley. If that's the case, then we'll make them show up again.
-2 if you want to.
Mhm.
Create the F double prime sign if you're like using the F prime graph.
Yes, you can. I would build the second derivative graph, sign line first before you do your second derivative graph. Sorry, yeah, build this first because this is easier to look at when you're building your second derivative graph. Yes,
How do you know what's over the second derivative?
the peaks and valleys, the max and mins. Yeah, the relative max and relative mins of the F prime graph will show up on the original graph as points of inflections.
And then the F
F prime, it's just the x-intercepts. Yeah. Okay, so before we didn't want to look at the movement of the graph. We just want to look at above and below. But now we want to look at the movement. A negative slope on the F prime graph means a what on the means concave what? Yeah, down. Yeah. Don't look at the curvature, right? The curvature is not going to match because this is not the original graph. So what looks like a concave up is not necessarily concave up because again, this is not f of x, this is f prime. Now, if those f of x, then that will be true. Any shape that you see is the concavity that you would expect. But here, look at the slope. So negative slope, concave down. Positive slope means concave up on the original. Negative slope just keeps alternating, right? Okay, this is the hardest part of this process. Are we okay building these two sign lines? Yeah.
It makes it up, but like this. I thought it was like when it's a negative y value. Yeah.
Well, when it's a negative y value, that's going to mean negative slope.
Negative slope. Okay.
Negative slope. So concavity is dealing with the movements, right? So if my slope is becoming more negative, then the graph is going to end up looking like it's part of a concave up or a concave down graph.
The increase and decrease.
Increase, decrease, right? Your increase, decrease is going to translate to the proper concavity on the original graph. Okay. Any trouble here? Because if we're having trouble here, I want to know so that I can help answer those questions. Yeah.
So like, I'm just confused how you know if it's concave down.
So you look at the slope. So the negative slope on the F prime graph is going to mean a concave down. A positive slope on the F prime graph will mean concave up. Yeah. Yes, that's right. We don't do any concavity information on the first derivative sign line. Oh, wait, what's your question again?
But you said like on the second below the X axis.
Right, yeah. Well, when we build the second derivative graph, then we'll label them. Yeah, but the way you read your concavity is based off of the slope of the F prime graph. Everybody good?
This is the first step you start off with.
This is the first step, right? And I'll give you an F prime graph. The first thing is get those sign lines going. Okay, so now what I want us to do is cover up your F prime graph, because if you're looking at this graph trying to graph your f of x, you're gonna end up copying that. So let's cover that up if you can. So let's do part H first, right? Because A through G, we're just listing properties that we've already built. Okay, so we're going to sketch the f of x graph. We have two starting points. Let's go ahead and plot those points. And we're going to do a sketch, and then I'll talk about how that range is going to affect us. So we're going to do it lightly because we have to do some changes. Okay, so order pair -5, -4. Order pair 5, 3. Okay, we're going to start here and end here. Now, we're only going to look at the F prime graph because that's going to help guide us. We're just going to do what the arrow tells us. If the arrow points up, we're going to make the graph go up. If the arrow points down, we'll make the graph go down. If it hits a slope 0, then we want the graph to flatten out. Okay. So what do you want the graph to do at the beginning? Just start what? Start rising until it hits to some y value of -3. We don't know what it is, but we do know there's a slope 0. So it'll level off for a moment and continue rising until it hits a relative max at -1. Yes.
The negative, I thought the negative here is X,
What's what?
an X value.
It is, yeah. So we have to pick a y value to target. So we don't know what the y value is. Just pick a y value and then just continue rising. Okay, so -1, I'm going to target a point that is relatively high. So maybe how about this point here? And then I got to go down to a relative min at 3. Again, that's just the x value. I got to pick a y value to target here. So your graph may be higher or lower than mine, but do your shape match?
See, it like bends a little bit at -3.
I'm sorry?
It like goes sideways a little bit at negative.
Yes, it does. Yeah, because it's a slope 0. So I do want to kind of let it flatten out for a moment and then rise again. Okay. So is our graph more or less matching? Now, before we continue, this is where the range is going to come into play. What does the range tell us? What does that mean?
It's kind of like a transcription, you know, like left 7 down, up 5. The lowest point 7.
Lowest and highest what? Y values, right? Lowest and highest Y values. Now, these are set in stone. So what could we do to force the graph to have a lowest Y value of -7 and the highest Y value of 5?
Bring the 2 endpoints down.
The endpoints, we can't move them, right? The endpoints, we're already told what those endpoints are.
The curve.
Yeah, we can move the max and mins to the right places, right? So we can drag this point all the way down to what?
-7.
Yeah, 1, 2, 3, 4, 5, 6, 7. So we may have to do a little bit of erasing here, but we're going to keep the same shape, right? We're just making a slight adjustment. We're not doing much change overall. And we can move the max to what? 5. So I kind of have it there already. I'll just make it so that I'm showing that 5. So that's what we didn't do yesterday. This is the new thing that I want to talk about, how once you do your dotted line sketch, look at your range and kind of push and pull on your max and min until it kind of fits into that interval. Okay, are we good here? Okay, so now we're going to see wherever your graph lands at -3, -2, 1, and 4, go ahead and plot that point because that's going to be your point of inflection. The Y value doesn't matter as long as wherever the graph lands at -3, go ahead and plot that point. I'm going to highlight those points there. So -3 here, -2, +1, and 4.
Why are those points?
Because those are my points of inflections.
Oh.
Those are places where my graph is going to change curvature.
Okay, so we haven't really done the,
Not yet, not yet. That's the last step coming up. We're just going to connect the dots with the proper curves. Okay, so we're going to start off with what? Concave down, but just showing a portion of it, right? We're not doing a full concave down because we're just reaching that point, and then we gotta switch. Okay. Next up, we switch to concave up. Back to
they're done.
back to
They're done.
concave up. Finally.
They're done.
So I'm just kind of over exaggerating those curves to make it fit. You don't have to erase your dotted line. In fact, I like seeing that because then I see that you're kind of progressing to the next step.
You sort of do that at double prime.
Yeah, we still do f double prime, but are we okay with f of x?
Can we just arrange for that double prime here?
Nope, I'll just ask for the range on the f of x graph.
I thought that was the X double prime graph.
No, this is my f of x graph. My f double prime graph will look a little different
So why do we do concave up?
because we are putting the curvature into the original graph. Right. Now, concave up, concave down will look a little different on the f double prime graph. It'll be location. We'll be back to location. Okay, are we good? But look at this, right? If we're looking at the f prime graph, trying to get our f of x graph, we're gonna end up copying it. So, so it's good that we cover this up, right? So we just are making our graph appropriately. Next up, let's sketch our f double prime graph. So f double prime graph, we're only going to rely on our f double prime sign line. So in fact, I'm going to cover up both of my graphs because I don't want to be looking at them to sketch my graph. Which is the only thing I'm using here. Okay, let's label what are we dealing with here. Because our y-axis no longer represents position, it doesn't represent slope, it represents concavity. So above the x-axis means where my original graph is going to experience concave up. Below is concave down. On the x-axis is point of reflection. Right? How can we start off? What can we place onto the second derivative graph? Endpoints. Okay, what else? X-intercepts, right? So -3, -2, 1, and 4. Hmm?
Not put partial points.
1, 2, 3, 4. I did. But I'm not plotting that point, right? That 5 is not an x-intercept. But I did get that marking there. So where do we want our graph to start?
We're going in like
So it needs to be above or below. Below. But it's got to reach this point, right? So these are nice anchor points because we know our graph will have to thread through those x-intercepts. So make the graph as simple looking as possible. Don't try to match the shape. The shape is for the original function. So just make it as simple as you can. Make it rise up to that point. What's going to happen between -3 and -2?
Go up.
Go up, but then it's going to have to come back down. Now, some students have trouble with this because they're looking at this going, wait, this looks like concave down. So, but then I'm asked to do concave up. Don't look at the shape, look at the location, right? We're doing this location, but I have to make it loop down. So that's why it looks like a weird shape that's opposite, but we're in the right location. We're still above the x-axis. Okay, and then between -2 and 1,
Go down and back up.
yeah, go down, back up. And then between 1 and 4, go up, come down, and then between 4 and 5, go down.
Down. You don't care about how big the curves are, right? Like, you know, on your graph.
I'm sorry?
You don't care about.
No, I don't. Right. It doesn't matter how your curves are. Okay, so one thing to check is that your function, your f prime and f double prime are all looking different, and they are, so that's a good sign. Okay. And I skipped A through G. Are we good with those? Being able to pull from our sign lines and writing all of our because statements.
So this is like, like the unions.
Yeah. So things like this, right? So being able to write your relative max, relative min, and then being able to write your because statements. I'm looking for that on the test.
What do we want like this on the test?
Yeah, it'll be pretty much like this. Yeah. It'll just be a different F prime graph, but things I'm asking will be, I may ask you for relative min instead of relative max. I may ask you for concave down instead of POI, but everything you just pull from your sign lines, right? That's everything's in front of you.
So you should do those questions like after you do algebra. Like A through G.
Yeah, it's up to you. I just wanted to go over the problems, the parts that I feel I wanted that I needed to help you see, make sure they understand, because I know that you guys are good. Hopefully, you guys are good with this, right? If you have the sign lines correct, then you're just pulling information. Right? As far as the order that you want to do it in, I will say though that I'd like to do my f of x graph first, get that out of the way, and then do my f double prime graph. But definitely do your sign lines first. Right? Your sign lines is kind of is your way to get everything that you need.
Yeah, second derivative test.
Yeah. Second derivative times 2. So if I give you a second derivative test problem, it'll look like this. So if f of 2 equals 6, if f prime of 2 equals 0, and if f double prime is equal to negative 67, what can we conclude about the graph at x equals 2? Which is it? Relative what? Relative max. Okay, so this is my order pair. My order pair has a slope 0, and my order pair has concave down. So there's my points. Slope 0 just means it could be a relative max, it could be a relative min, it could be neither, but this is telling us exactly what it is, right? This is not this is not a number on the graph. This is a curvature value. Okay, don't worry about that number. Worry about the fact that it's negative.
Concave down.
Concave down. So f double prime 2 is less than 0. Concave down. If I force the concave down through that point, then the only conclusion I can make is that point must be a relative max. So that's a second derivative.
And you assume it's like slope, and then slope 0 tells you that's like
That it's a smooth curve, right? Huh? Well, it doesn't have to be a full concave down. It just have to be a concave down through that point. Because it's a slope 0, right? The only place that I'm going to have a slope 0 and concave down is at these points, right? There's no other places where there's a slope 0 and concave down. And there's no point above this because it's a function, so I'm never going to have two overlapping graphs. And if this is a positive number, then what does that tell us? That it's a concave up. If it's concave up, then there's a relative minimum.
So like you wanted to, like, you're not gonna ask us like solve the numbers.
Nope, it's like, yeah. If I give you one, it'll be like this. Okay, why don't we do a problem from the function level? So this one is more straightforward. Mr. Fuller went through the problems like this, but, oh wait, you guys finished this problem already? We did. All right, any questions with it? Okay. So let me just run through it, make sure that you guys are comfortable with this process. And also you can put this in your calculator and also see the graph and help confirm information as well. But if you're starting at the function level, then you just find f prime, set f prime equal to 0, and you just go through the first derivative test like you normally would. Set f double prime equal to 0. Go through a concavity test like you normally would. And then you will pull all the information from the function and f double prime sign line. And then you just sketch your graph exactly like what the arrows are telling you. And you can also use your calculator to confirm your order pairs. So I feel like I didn't go over these as much because I felt like these are more straightforward but you'll see a problem like this. It'll be a polynomial. This should be an easy one.
It's like doing characteristics again.
I'm sorry?
This is like listing characteristics.
Yeah, listing characteristics. And then sketching the graph.
Just the FX.
Yeah, just that's right, exactly. If I gave this problem to you, it'll just be F. I was just going to ask you for FX graph. That's right. Okay. Let's see. How about we do optimization problem? Okay. So I kind of ran out of problems to do in the packet, so let me create one, and you can just put this on a separate sheet or find any space that you can find. Okay, rectangular box with closed top has a volume of 20 cubic meters. The length of the base is 5 times the width. Material for the base is $20 per square meters. Material for the sides and top is $4 per square meters. Find the cost of the cheapest container. All right, so we know that we're working with surface area. Surface area and cost are going to go together, and that's ultimately what we're trying to find the derivative for. You know the volume is going to be your supporting equation. So I know that the length of the base is 5 times the width, so I can call one side X and the other side what? 5x. And then my height is unrelated to the base, so okay. Volume. We can come back to that. We need it. Now we can build our surface area equation. Surface area. We're going to add up the area of all 6 of our surfaces since this is a closed top. What is the area of my base?
So 5x squared. 5x squared.
And then there's another 5x squared, right? Okay. What's the area of my larger vertical side? And then there's also another 5xh. And the smaller
plus xh.
Yeah. Okay, there's cost associated with each of the sides. The base is the most expensive. So we have to multiply $20 into that. Now, in this case, looks like the top and the sides are of the cheaper material. So all this is going to have to be multiplied by 4. So here's my cost equation. I'm going to separate these together because these are not like terms, right? So I'm going to separate the top, which is $4, and then the size, which is another $4. Yeah.
Is it the box open?
This one I have being a closed
Oh, it's
top.
closed. Okay.
Mhm. But yeah, if it's open, then there would not be the second 5x squared. So 5 plus 5 plus 1 plus 1 is 12. Okay, so $20 for the base, $4 for the top, and $4 for each of the sides. Okay, continue combining like terms here. All right, so my cost equation is as far as I can get to at this stage. I do want to find the derivative for cost, but am I ready for that?
No, you gotta do height first.
Yeah, I need to find height, and height's going to come from my volume equation. So this piece will go in. This is where I want to be before I jump into power rule. C prime equal to 0, and now I just solve for x. Then I can take my X value and insert it in for my cost equation because it's asking for a minimum cost. Okay, help session Friday morning, help session Monday morning, but tomorrow I'm going to start the next unit. All right, come get your phones. Yeah, I changed that to Monday.
I'm confused on this, because I was getting this one, and I looked at the interview, and you somehow got -25.
Oh, -2.5. That's just decimal value. That's the motion.